Welcome to Unit 2, Lesson 2. We're going to begin in this lesson and the next creating another list of identities or formulas that we're going to be using. So before we begin delving into this topic, what I want to make clear is that the formulas that we're going to learn in this section, they do not need to be memorized. Now, I will think that of all of them, I think a lot of you, well, there's kind of like a little chant that people can use when we do sum and difference formulas, but you will be provided a reference sheet that will contain these formulas as well as the formulas that are in Lesson 3 as well. Please note that they will not be given to you on your AP exam, but to be transparent, memorizing them today doesn't ensure that you will know them on the AP, and we want to know how you can apply them. And as you continue in your study of calculus, as these formulas come up in your work, I think that that will be a natural way for you to to learn them. So again, we're going to continue. We're going to learn some advanced trigonometric formulas or identities. And to begin, I want you to consider y equals the cosine of x plus 2. And if I brought somebody in who maybe wasn't an honors pre-calc student, like an algebra 2 trig student or an algebra 1 student, maybe their natural reaction would be, oh, I'm just going to distribute, right? We see those parentheses and we want to distribute. And I want to debunk that. This is not correct. Why? Well, let me give you some more concrete problems. Let's talk about finding the cosine of the sum of two angles. I'm going to pick pi and pi over 2 because those are pretty easy to calculate. So if your conjecture is, I think that this is equivalent to the distributive property, all right, let's explore that. Well, we know on the unit circle that the cosine of pi is -1. We know the cosine of pi over 2 is 0. Their sum is -1. However, if I add the cosine of pi plus pi over 2, we essentially get 3 pi over 2. And 3 pi over 2 is the point 0, -1, and its cosine is 0, and they're not equivalent. So this is one counterexample, and hopefully a way to debunk that you cannot distribute. If you're trying to take the cosine of the sum or difference of two angles, the distributive property doesn't apply. So what formula does apply? Well, we're going to prove it. And I like to do this proof. If you go online, there's going to be several proofs that you can look at. I've chosen a geometrical approach because I feel like it is the most visual. This is not the only way to prove it. And I've always have a student in class that's like, just give me the formulas. I believe you. I believe you, you're the teacher. Not as honors kids. And really not in your study of mathematics. We should know why and where these formulas come from. So I am having you turn in these notes just to make you accountable, but please know I'm not going to ask you to reproduce this on a test or a quiz. And your inner math nerd might actually like it. Okay, we first have to kind of digest this picture before we actually start the algebraic proof. Here's what we have going on. I am going to assign that this angle EAF, is alpha, and I'm going to assign that angle BAE is beta. So notice that we're going to prove the sine of alpha plus beta. So when I add them together, I get angle BAC or BAF. So you can see the sum of the two angles in the picture. All right. So now this is what I need to convince you. I need to convince you that this angle DBE, is alpha. And once I do that, this proof and the remaining proof should go fairly quickly. All right, here we go. If I highlight DDE down to A and F, and I'm going to redraw it to the side. So D, E, A, and F. Well, I have marked that this angle is alpha. Well, this angle would also have to be alpha by alternate interior angles. So I put it back in. So it's angle DEA. DEA is also alpha by alternate interior angles. All right, now, the next part I want to look at is I want you to look at AEB. That is a right angle. It is a right angle because you were given the right angle symbol for on that right side, so that means that is a right angle as well. So if I redraw it to the side, right? This is angle alpha, this is DE, and we have A way down here. Well, if this angle is 90 degrees, that means this has to be a complement. So the way that we can talk about, let me get rid of some of this. All right, so again, if this is alpha, then its complement right here has to be 90 minus alpha, right? If alpha, let's say alpha was 30 degrees. Well, then that means the purple angle would have to be 60 degrees because 90 minus 30 is 60. All right, so last, I want to look at the fact that you have a right triangle up here, which is triangle BDE. So we know that angle D is 90. We know that that angle E is 90 minus alpha. Well, the sum of the three angles, B, D, and E, have to be 180. So if I take angle D, which is 90, plus angle E, plus the measurement, let's go ahead, plus the measurement of angle B, that has to be 180. Well, 90 plus 90 is 180. That cancels that out. So the negative alpha plus the measure of angle B is 0. Add alpha to both sides to solve for the measure of angle B. So the measure of angle B has to be alpha. So hopefully, again, if you need to, remember this is a video. You can always stop. You can go back. But it is going to be important for our proof that angle EBD is also alpha. All right, here we go. Here's the proof. Here we go. Let's begin. All right, we want to know the sign of angle alpha plus beta. Well, this angle BAC is alpha plus beta. All right, and if hopefully you can see where I'm kind of highlighting this triangle. All right, the opposite of angle plus beta is segment BC. And the hypotenuse of that triangle would be AB. All right, so now let's consider that if you look at the opposite side, B to C, it consists of two segments that I can add together. BD plus DC all over AB. So that's by segment addition. Now, in the next step, I want you to look at DC. DC is not a particularly helpful segment because DC is not a side of a triangle, but it is congruent to EF, which is the side of a triangle. So I'm going to rewrite this statement as BD over AB, give it its own denominator, and I'm going to replace DC with the congruent segment EF. Again, why did I do that? Because EF is the side of a triangle and DC is not. All right, next. This is what I consider to be the maybe not as intuitive part of this proof. I'm going to write BD over AB. I'm going to leave a little bit of a space on purpose. Let me go in and rewrite that beta. Okay, we need to find a segment that has a relationship between BD and AB. And if we were in class, I would probably let you stew over it for a few minutes and we would discuss it. Since we're on a video, I'm going to cut to the chase. That side is BE. BE is the opposite side of beta, and it is the hypotenuse of BDE. So I can multiply anything by 1 and it stays equivalent. So I'm going to multiply by BE over BE. We're going to do the same thing now for EF over AB. We need to find some type of segment in this picture where EF and AB both have some type of relationship with this segment. Again, if this was a classroom situation, we would stew over it, but that segment is AE. It happens to be the hypotenuse of the red triangle and the side of the blue triangle. Okay, so what are we going to do next? Multiplication is commutative. So I am going to flip-flop those two segments. I have BE over AB times BD over BE plus, again, commutative property of multiplication, AE over AB times EF over AE. And if you're wondering where are we going with this, here we are. We're almost at our formula. We really are. All right, so let's do some highlighting. If I look at BE over AB, look at the blue triangle. What ratio is that? Well, that is the sine of beta. Now, let's look at BD to BE. Now, recall, we said that this is angle alpha up there. So if we look at it with alpha, that's an adjacent BD side to its hypotenuse BE. So this is the cosine of alpha. All right, let's do it again. AE to AB. Look at the blue triangle. That's an adjacent side to beta and the hypotenuse. So we've got the cosine of beta. And now if I look at EF over AE, EF is the opposite side of alpha and the hypotenuse. So that gives us the sine of alpha. Now, if you want to look at how it is printed in your notes all pretty, this is a term, this is a term. So I can swap the terms by the commutative property of addition, and I can put the sine of alpha first by the commutative property of multiplication. So we get sine alpha cosine beta plus sine beta cosine alpha. And if you want to sneak ahead to the end of your notes, what we just proved is what I have highlighted in green. We have the sum and difference formulas. So I used A's and B's, they used U's and V's, but we have sine, cosine, cosine, sine. Remember that little chant. Sine, cosine, cosine, sine. This is also true. I'm not going to prove this in the video, but you will get a very similar proof with opposite signs. So it's always sine, cosine, cosine, sine when we are doing a sum or difference of sine. Notice how the operation stays the same. So that's how I remember it. Sine, the operation stays the same. And we just alternate the U and the V, the U and the V. So the first angle, the second angle, the first angle, the second angle. So now let's do cosine. All right, when we do cosine, we've already established that that angle is alpha. Here's my beta. All right, so let's talk about the sum of the cosine. So here is the sum. Angle BAF is the sum of alpha plus beta. If I want to find the cosine, again, if I highlight angle BAC and then look at BC, there's a right triangle, and the side adjacent to that would be AC, and the hypotenuse is still AB. Now, if we look at side AC and actually look at that whole segment AC to F, this is where it changes. When I want to look at AC, it's not going to be the sum of two segments, it's going to be the difference. So this means we can represent AC as segment AF, the total, minus CF, the part, all over AB. But just like we had in the sine proof, if we look at CF, CF is not particularly useful. CF is not the entire side of a triangle. But you notice we've got a rectangle DEFC in the picture, and so CF is going to be congruent to DE. So we're going to substitute that value because DE will be a little bit more useful. It's the side of a triangle. So let's give AF its own denominator of AB, and we're going to subtract off not CF, but its congruent part DE over AB. So it follows similar to the sign proof. Let's look at AF over AB, and let's look at that ratio and see what they have in common. So if I look at AF and I look at AB, what is a segment that they both have in common? Well, that's segment AE. It's hypotenuse to the AF side, and it is a side to the hypotenuse of the AB side. So we're going to go ahead and multiply by 1, because as long as we multiply by 1, we stay equivalent. And I'm going to multiply by the measurement of AE over AE. So now let's look at DE over AB, and let's kind of do the same thing. Let's look at these segments and see what they have in common. So I'm going to look at DE, which is that small segment in that right triangle at the top, and then you have AB. Well, the segment that they have in common is going to be BE. So again, we multiply by 1, so it stays equivalent. And again, you're seeing kind of similar algebra. We're going to use the commutative property of multiplication to flip-flop those so that we have AE over AB times AF over AE minus, let's flip-flop, BE over AB times DE over BE. And now let's look and see what ratios we have. All right, so when I look at AE and I look at AB, those are both on the blue triangle. So I notice that that is going to be adjacent over hypotenuse. That's the cosine of beta. Now let's look at AF to AE. Those are both on the red triangle, and AF is also adjacent, so that is the cosine of alpha. So now let's look at BE over AB. Those are both on the blue triangle, and BE is opposite beta, so that's the sine of beta. And then if we look at the last, keeping in mind, remember that is angle alpha. When I look at DE to BE, that's the opposite of alpha over the hypotenuse, so that gives us the sine of alpha. So when we look at this typed all nice and pretty in the print, we do go ahead, and since alpha was the first angle and beta was the second angle, it's usually written, we can do the commutative property of multiplication, it's usually written as cosine alpha cosine beta minus, again, let's use the commutative property, sine alpha sine beta. So let's go ahead and kind of fast forward into your notes a little bit. And we, again, I didn't do both. I just proved the sum. I'm going to leave the difference for you. But one thing that I do want you to notice is, unlike the sine where the operation is the same, the operation for your sum or difference of cosines is always opposite. And this is a little chant. I know it seems a little goofy, but this is kind of a chant that oftentimes the students will use to kind of remember. I know you don't have to memorize, but this is just how the kids remember them. And it kind of goes like this. Sine, cosine, cosine, sine, cosine, cosine, sine, sine. Do it one more time. Sine, cosine, cosine, sine, cosine, cosine, sine, sine. And it's a way that kids remember, because sometimes having to look stuff up all the time is a little laborious. And I will let you know that if you know these sum and difference, in the next lesson, we're going to talk about double angle. We're going to talk about half angle. We're going to talk about power reducing. And if you know those, you can derive all of those fairly easily. All right, so now let me erase, since I've marked all of this up, and kind of clean it up. The last part of this video, we are going to derive how we get the tangent of the tangent of the sum of two angles. Again, it would be a pretty analogous if it was a subtract. You'll notice in your notes, you're like, hey, no picture. Well, that's because we can consider this to be the sine of alpha plus beta over the cosine of alpha plus beta by quotient identities. If you don't like alpha and beta, then use A's and B's. You can use X's and Y's, really whatever variables you want. So let's expand these using the sum and difference formulas we just used. And this is where that chant comes in helpful. Sine, cosine, cosine, sine, cosine, cosine, sine, sine. The first angle is alpha, the second one is beta, and all you do is alternate them. And remember, because the sine is the same operation, we have a plus, therefore cosine is an opposite. Now you might be looking at this going, where are we going to go from this? And this is where we're going to cheat a little bit. Look at what we have now, okay, and look at where we're headed. Especially look at that denominator. How do we make that a 1? Wouldn't we divide by itself? Wouldn't we divide by the cosine of alpha, cosine beta, in order to make this part of our formula a 1? So I can go ahead and divide by the cosine of alpha, cosine beta, but then I have to do it to all of those terms. So this is going to look slightly awkward, but mathematically, in order to do that, you can only multiply by the number 1 because that is the multiplicative identity. So this is what that looks like. In order to really divide every term by cosine alpha, cosine beta, you're really multiplying by 1 over cosine alpha, cosine beta, over 1 over cosine alpha, cosine beta, where this is your main denominator. So this is a lot of writing. It's up to you if you want to write this down, but watch what happens. When I take this term and I multiply it by sine of alpha cosine beta, that looks like sine alpha cosine beta over cosine alpha cosine beta. Again, we're just dividing all of the terms by cosine alpha cosine beta. When I do it to this term, we get cosine alpha sine beta all over cosine alpha cosine beta. Again, main denominator. When I take it and I multiply it by the first term, we get cosine alpha cosine beta over cosine alpha cosine beta. And then I have subtracting sine alpha sine beta all over cosine alpha cosine beta. All right, so what do we get from all of this? We get our formula. We're done. Sine alpha over cosine alpha gives me tangent of alpha or tangent of the first angle. The cosines cancel. The cosine alpha over cosine alpha cancels, and I am left with plus a tangent of beta. All of that cancels, and you're left with the multiplicative identity of 1 minus the tangent of alpha times the tangent of beta. So that is where we come up with that sum of a tangent formula. So I hope you enjoyed learning how the sum and difference formulas are derived. Please now go on to the next video or assignment, and that is how you will learn how you actually apply them to do some homework problems. Enjoy.